Hi, everybody. Let me just find my cursor. It's my constant problem. Okay. Welcome. I'm Angela Jensvold, and we are going to finish reviewing circular motion. I gave you the easiest homework on Earth last night. Let's go over it really quickly. It just asked for the direction of the acceleration. So in a circle, acceleration is toward the center of the circle. So I hope you got that. Now, what does it say? Is it going? Oh, actually, there is more to it. Okay. That's just the radial component, right? It's going counterclockwise. So counterclockwise is this way. And the angular speed is BT. So that means as time goes on, the angular speed gets bigger. So it's also going to have a tangential component and a radial component. So when you add those two vectors together, actually, the acceleration points like that. Okay, so it wasn't as easy, but it was still pretty easy. I hope you guys were able to get that. Okay, so today we're going to look at two learning objectives, interactions D&E, 2D&E, derive expressions relating centripetal force to the minimum speed or maximum speed of an object moving in a vertical circular path. So vertical circular paths, and then same thing for a banked surface. Okay, so those are our two things we're going to look at today. We do need to finish up a couple things that what got cut out yesterday because of the technical issues, but then we'll do those two scenarios. Okay, so the main idea is centripetal force is just the sum of forces in the radial direction. So sometimes people think centripetal force is a separate force like normal or friction. It's not. Centripetal force is just the sum of forces acting on an object, okay, when it's going in a circle. So centripetal force is the sum of forces in the radial direction. When looking for the maximum speed of a car going over a hill, the condition you're looking for is zero normal force. So zero normal force is right at the boundary when the object will lose contact. Let's say it's a car. The object will lose contact with the road. And then for banked curves, if you remember yesterday, we had both friction and normal, both have a component that's toward the center of the circle. Okay, yesterday we did this problem and I was supposed to solve for the coefficient of static friction, and instead I solved for velocity, which they had already given you right here. So let's try it again. You always start with a force diagram. I'm going to do this a little bit quickly because we did it yesterday. So the force that's keeping it in the circle is force of the ground on the car. You use Newton's second law in the radial direction. You know radial acceleration is v squared over r. So you have friction of the ground on the car. And then friction is mu normal, right? Mu times normal of the ground on the car. Okay, now we need to draw a force diagram from the side, okay? So we did the overhead view force diagram, forces in the radial direction. Now we just need to check out force of earth on car and normal force of the ground on the car. When you look at that force diagram, well, I was trying to make them equal. Let me try it again. I mean, technically it should go from the center of mass. I'm not that picky right now. Okay, so we have two forces in the vertical direction acting on this object. And when you look at that, you can see that those two forces will be equal because it's not accelerating in the vertical direction, right? So that means that normal in this case will be equal to the force of the earth, which has a magnitude of mg. Okay, but you have to do that every time. You can't just blindly say normal is mg because oftentimes it's not. You could be on an inclined plane. Remember yesterday we had the vertical wall that was providing the normal. Okay, that normal was not equal to mg. We're gonna come back to that today actually. Okay, so now I'm gonna come over here. V squared over r equals mu mg over m. M's cancel. This is where I took a wrong turn. I took a path that should not have been taken. Just solve from you. V squared over RG. That's it. Okay, so it was just in my very last step, I solved for the wrong variable. Now I think we've got it. Okay, here we go. You've got a cart of mass m and a load which also has mass m, and the cart never loses contact with the hill surface, and the speed v min is the minimum speed necessary for the cart and the load to leave the surface of the hill at the top of the hill. So if the load is removed, what is the new minimum speed? Okay, give it a try. Okay, I hope you guys started with a force diagram. Let's draw the thing at the top. Okay, so what are the forces acting? There's the force of the earth on the cart, and then you have the normal force of the ground on the cart. Is there another force here? So a lot of times students will want to say, yes, there's the force pulling it out of the circle. Okay, so if there is, now you have to use my subscripts. They're annoying. I'm sure you find them annoying, but this is why I do it. So what is the outward force? Every force is an interaction between two objects, right? Tell me what the object is that's pulling this thing out of the circle. Is there something pulling it out? If you imagine a ball on a string and the tension is pulling it in, right? Some people think there's an outward force. So this is string on ball. What is that outward force? What object is pulling it out? If you whirl a ball or on a string, what's pulling it out? If you can't identify an object that's pulling on the ball, then there's no force. Okay, so let's get rid of that. I don't even want it there. Get rid of this one too. Now, also, sometimes people say the force of the motion, the force of the motion. That's why I use these subscripts. If you think there's a force of the motion, what is pushing that ball tangent to the circle? Tell me an object. What is it? Right? Silence. I hear silence from you. That's because there's no object pulling it tangent to the circle. So you can't just write force of motion or whatever. I really think that's why I use those subscripts. Every force is an interaction between two objects. Okay, so we're not going to do that. We're not going to bother with that. Okay, that's the same thing, by the way. I'm not quite done with my rant. People want to say tension, string on ball, right? And sometimes people will say, oh yeah, and the centripetal force, right? They want to put centripetal force. Okay, fine. Tell me, what is the object pulling on the ball? People will say, the string. Oh, but I already have that. That's a tension, right? Okay, and if you're going to add another force called centripetal force, what's the object? Do you see what I'm saying? So centripetal force just means the sum of forces. Get this thing off here. Get this. Well, I just erased the whole thing. The only force in that scenario was the tension in the string, okay? All right. I think I'm done. I think I'm done with my rant. Okay, so we got to find Vmin. All right, you know what's next. We just did a force diagram. Now we got to do acceleration in the radial direction is sum of forces in the radial direction over mass. That's Newton's second law, right? Okay, now read this last sentence. The speed, Vmin, is the minimum speed necessary for the cart and the load to leave the surface. What does leave the surface mean? What would normal be if you left the surface? So radial acceleration would normally be the force of the earth, which is mg, minus normal of the ground on the cart over mass. But the thing is, if it leaves the surface, normal is 0. Okay, so you get radial acceleration is just g, right? And that's v squared over r, by the way. This corresponds to the minimum speed. As soon as we plugged in normal as 0, our velocity is the minimum speed. So v min is the square root of rg. Okay, well, we should use capital R, you guys. They gave us capital R, that's a value. So we need to plug in capital R, okay? Because then we're making it specific to this situation. Be careful with that. Okay, this is a doozy. I think I'm going to give you, oh, I'm only giving you a minute anyway. It's okay. Okay, so what are we looking for? Constant speed. How can we find speed? We need to get the two components of velocity and use Pythagorean theorem. So let's find, for option A, let's find Vx, negative omega A sine omega t, and Vy is omega A cosine omega t. Okay, we have the two components of the velocity. So to get the speed, we would do square root of Vx. Vx squared plus Vy squared. So we'll do omega squared A squared sine squared omega t plus omega squared A squared sine squared omega t. Okay? If you pull out an omega A out of that square root, you would get omega A, because sine squared plus cosine squared equals 0, right? And the square root, whoa, sine squared plus cosine squared equals 1, and the square root of 1 is 1. So this is your speed, and it's constant. But there was another, they also want non-zero acceleration that's constant. So to get acceleration, you have to differentiate velocity. So let's get going. What would this be? Negative omega squared A cosine omega t. Ay is negative omega squared A sine omega t. And then to get the magnitude of acceleration, you would do square root of ax squared plus ay squared. So you get omega to the fourth a squared cosine squared omega t plus omega to the fourth a squared sine squared omega t. If you pull out an omega squared a, excuse me, if you pull out an omega squared a, then you're left with the square root of cosine squared plus sine squared, which is 1, and the square root of 1 is 1. So is the acceleration non-zero? Yes. Is it constant? Yes. Thank goodness the answer is A, because we do not have time to do B, C, D, and E. You can do that for fun later on your own to rule them out for sure, but A is the answer. Okay, this is a really good question for this year's exam. Why don't you guys try it? Okay, I hope you guys drew a force diagram. On the right, you have the side view, and read this last sentence carefully. Forces on the rocket. That's basically the main problem, okay? We want the forces on the rocket. So starting on the rocket, pointing toward the right, you have tension of the string on the rocket. You have the normal force of the ground on the rocket. And then you have the force of the earth on the rocket. Okay, now from the top view, you have tension of the string on the rocket. And then you have, they're calling it thrust, but I've already used capital T for tension, so I'm going to use force of the gases on the rocket. Okay, even if you don't look at the labels, which of these matches the diagram? This one and this one. Look at this. What are they doing here? They're doing the tension. They're basically saying that would be the tension on this pin. Like, I guess maybe if there's a pin right here, maybe holding that string in place, that would be the tension on the pin. And same thing here, they have tension pulling to the left. That would be the tension on this pin. But we want the forces on the rocket, so you have to be careful. Okay, find the magnitude of the acceleration. Okay, you see how it's slowing down at the rate of 1.2? So that means the tangential acceleration is pointing opposite to the velocity. And then it also has a radial component of velocity, which is v squared over r. And you can plug in v, which is 36 meters per second squared divided by the radius, which is 1440 meters. And that works out to be 0.9 meters per second squared. And then the tangential acceleration is 1.2 meters per second squared. So if you make a triangle to get the overall acceleration, or not a triangle, but a parallelogram, you want to get the diagonal. So you would do the square root of 1.2 meters per second squared plus 0.9 meters per second squared. And I think you get 1.5. 1.5 meters per second squared. And it just says magnitude, so it's not asking for direction. We know the direction, don't we? Because we wrote it out on our diagram, but. Okay, can you guys compare the acceleration of A to the acceleration of B? Okay, so the car at A has a tangential acceleration A. We don't know if it's speeding up or slowing down, so I'll just draw it as if it's speeding up. I suppose if you're going over the top of the hill, you should probably be slowing down though, right? Okay, just for safety's sake, I'm gonna erase this and I'm gonna set a good example for the young drivers. Okay, so you have a tangential acceleration of A and a speed of V. That means the radial acceleration is V squared over capital R. They gave us the radius as capital R. We need to plug in capital R. Okay, now come over here to B. The car constant speed. That means no tangential acceleration. The only thing you have is radial acceleration, which is V squared over R. Let's plug in the V they gave us, V over square root of 2. So that'd be V squared over 2. And the radius is R over 2. What happens to these 2's? They cancel. And you get V squared over R. So this acceleration over here at A, acceleration at A, is square root of A squared plus V squared over R squared, capital R. Well, that's bigger than the acceleration of B, which is just V squared over R, right? Okay, so acceleration of A is bigger. Okay, so now we have a banked curve. So what I have here is like a vertical rod, and you spin this thing around, okay? You spin this thing around. The incline is frictionless, okay? The incline is frictionless. I put that up there. The incline is frictionless. If you spin it at a certain speed, the block will remain at a constant height on the incline. Okay, find the speed. This is a hard one. I'm going to warn you. Find the speed when the height of that block stays the same on the frictionless plane. Okay, go ahead. Okay, the key to these problems is to choose what your axes are. So I'm looking at this object and it's traveling in a horizontal circle, right? So what I would like to do is analyze the forces in the horizontal direction. If one of my axes is horizontal, the other axis has to be perpendicular to that. So it'll be vertical, okay? So AY, I want to do vertical forces and horizontal forces. I know that sometimes when you have an inclined plane, your axes are parallel to the incline and perpendicular to the incline. You could solve this that way. That's fine. I'm doing it horizontal and vertical because the mass is traveling in a horizontal circle. Okay, that's the radius of my circle. It's much easier to do it this way. Okay, so your axes have to be perpendicular to one another. The way people mess up these problems is they say, okay, I'm going to do along the radius of the circle, and then I'm going to do perpendicular to the incline. Well, it's all going to go wrong, okay? So make sure your axes are perpendicular to one another. Parallel to the incline and perpendicular for some problems, but for this one, I recommend horizontal and vertical because the circle the mass is traveling in is circle. Okay, let's go. What do we need to do first? I skipped a whole step. I skipped the most important step, force diagram. I'm going to try to draw it really big because I just feel like when all else fails, draw a bigger diagram. It really works. Don't ask me why. Okay, normal of ramp on block. And then we have the force of Earth on block. That's it, right? There's no friction. So I think that's it. All right, now we need to break up the normal into horizontal and vertical components, not perpendicular and parallel to the incline. We're not doing that. We've already said we're going to do horizontal and vertical. And I know you're used to doing it this way. That's where people get tripped up. Okay, so we got to do a little bit of geometry. Are you ready for that? What is this angle here? I'm not going to show you why, but it's theta. You're going to have to figure that out on your own later. That's more a trigonometry issue. I want to focus on the physics. So this would be normal sine theta, right? This component that's pointing toward the center of the circle, it's normal sine theta, right? And the component that is vertical would be normal cosine theta. I hope you agree with that. Okay. Okay, acceleration in the x direction, that's along the radius, isn't it? The horizontal direction is the radial direction in this case. Okay, and then the horizontal force is normal sine theta. Okay. We eventually want to find speed, but we don't know what the normal is. So let's go over here to our vertical acceleration. How is this thing accelerating in the vertical? Well, it's not, because it says that it's going to be at a constant speed. So 0 equals normal cosine theta minus mg. That's the force of the Earth. So that means normal is equal to mg over cosine theta. Now that we've got normal, we can plug it back in over here. It would be mg sine theta over m cosine theta. And then the m's cancel. That's nice. We're trying to find v, right? What is the radius of the circle? The radius of the circle would be this distance here, which would be L cosine theta, right? So let's plug that in. V squared equals L cosine theta times G times sine theta over cosine theta. Oh, good. The cosines cancel. And you get, well, you get square root of LG cosine, square root of LG sine theta, but we don't know what, so we don't know what sine theta is. Well, that's okay. No, they did give us theta. They gave us theta on the problem. Okay. So V is the square root of GL sine theta. It's kind of fun, right? You got to really put in the work in the beginning to make sure you're setting it up right. But then after that, it's like a puzzle. I don't know if you guys have been doing puzzles. I did a 750 piece puzzle. I think the puzzle industry is not suffering at this point. I hope you like that one. That's a banked curve. You can do it again, and you could try it with friction as a bonus. Why don't you guys try that with your teachers? Have it be a friction, an incline with friction. That would be a fun one. But the main issue with these problems are those axes, okay? All right, we're going to do a free response. All right, so I'm going to let you read this, and this is parts A and B, so I'm going to give you 2 minutes to do it. Okay. You guys want to try typing this? So you're going to have a choice on the AP exam. You could write on a piece of paper and upload it, or you can type it. I don't know which you prefer. For me, I prefer to type it because I would be a little bit stressed about uploading it. So let's just practice to see. I'm sure there's pros and cons of each, okay? But let's just give it a shot. Okay, I'm going to make a text box. Okay, derive an expression for the height of the ramp, h. Okay, so why don't we use our kinematic equation, v squared equals v, I guess I'll do capital V naught squared plus 2ax. Okay. But in this case, let's just say starts from rest. So you would have just v squared equals 2ax, right? But they said that the velocity at the bottom of the incline is actually called v naught. So I'm going to change that to v naught squared equals 2ax. Okay, well, we don't know the acceleration. You know what we need? So what I would do is I would have a separate piece of paper on my desk and I would doodle on it. So I'm going to do a little doodle here. I'm going to have normal of ramp on block, and then I would have the force of the earth on the block. So the component down the incline would be mg sine theta, because I'm going to call that theta. So I'll call this theta. So this would be mg sine theta, right? So then if we do the acceleration parallel to the incline, so this is an instance where you would want to do parallel to the incline. It would be sum of forces parallel to the incline over mass. So the acceleration parallel to the incline, which is the same acceleration we need for our kinematic equation, would be mg sine theta over m. So it'd be g sine theta, right? Okay, so let's just do equals 2g sine theta. You know, we named our angle. We don't have to name it theta. It's just out of habit. Let's call it b. How about that? Sine of b. I know maybe that makes you uncomfortable, but I'd rather type a capital B than a theta. Okay, 2g sine b times the distance, however far it went, right? And why don't we call that length of the incline L? So we'll call that L. Oh, I meant a capital L. Okay, 2g sine beta L. Okay, so, now let's go back and look at our angle. I'm going to draw it over here because it's getting kind of crazy. Here's L, here's theta, and they did define H. So what is H? H would be L sine theta, right? Oh, I keep calling it theta. It's such a force of habit. I'm going to go back. I'm going to call it B because it's easier to type. Okay, so H is L sine B, right? So sine of the angle, the sine, instead of sine of B, I'm going to write H over L. And then I'm multiplying by L. So what do I end up with? 2GH. What am I trying to derive? The height. Okay, now I'm going to solve for height. Height is V naught squared over 2G. I did it. I've got my whole derivation typed out. Okay. I'm the one who decided what to call the angle, right? So I called it B. Now the second question is, a short time after passing point P, the block is in contact with the wall and moves with the speed V. Once it's in contact with the wall, moving in the circle, is the vertical component of the net force up, down, or zero? So I'm going to label this B. I hope you guys said zero. 0, 0. because the object is not accelerating in the vertical direction. Is it accelerating in the horizontal direction? Yes, because it's changing its direction and it's changing its speed because there's friction acting on it. Okay, so I think that's it for this one, right? You know what we need to do? Let's look at the rubric. Oh boy, if I can find my cursor. This is the rubric that was used to grade this. So let's see how we did. For using correct kinematic and dynamic equations, 1 point for that. For substituting in correct values, so for substituting in V naught for the final, GH over L for sine theta, and L for the length. You can call the length of the ramp whatever you want. You can call it anything. It's going to cancel anyway, right? And then 1 point for the correct answer. As for the other one, you got 1 point for selecting 0 and 1 for a correct explanation. So does not accelerate vertically. Now I'll warn you that oftentimes we don't give a point just for selecting the right answer, okay? So normally we give the points for the explanation. So I don't think you should count on getting a point just for selecting the right checkbox, okay? It's going to be more in your explanation. So you really want to work on your explanations and don't assume that the reader, well, obviously it's not accelerating in the vertical direction. No, you have to say that. You have to say, why is the sum of forces 0 in the vertical direction, okay? If it were me, I might even go above and beyond and say it's not accelerating in the vertical direction, so the normal force of the table is equal to the force of the earth. That would be an A+ answer. Just, you know, to cover your bases. Okay, why don't you guys try these last 4 parts? I'm going to give you, I'm not going to give you 4 minutes. I'm going to give you 2 minutes. Sorry. Okay, I hope you were able to at least get a start. The first one says draw an arrow to talk about, to do the horizontal component of net force. I hope you put it in the 3rd quadrant. And then it says justify your answer. So let's type that here. Justify is very easy to type. So what are we doing? Net force. Okay, so there is a force from the wall pushing it toward pushing. I don't like the word it. If you can avoid the word it on the AP exam, you're going to avoid a lot of trouble. pushing the block, whatever it is, block toward the center, and there is a component of the wall's force slowing it, slowing the block down, right? So there is, okay, I think that's good. There's a force from the wall pushing the block to the center. There's a component of the wall's force slowing the block down. So the wall is pushing in two directions. It's pushing inward and backward. I think that's good. Now, determine an expression for the magnitude of the normal force. I'm going to try to do this by typing. So let's do acceleration. Acceleration in the radial direction is equal to sum of forces over mass. And we know acceleration in the radial direction. Oh, okay. So acceleration in the radial direction is, what are the forces in the radial direction? Just normal. And then if you solve, oh, and by the way, acceleration in the vertical direction is v squared over r. So normal, if you multiply by m, you get mv squared. Maybe I should put parentheses. mv squared over r. Okay, we just did part C by typing. We can do this. Part D, derive an expression for the magnitude of the tangential acceleration of the block. Okay, now we're going to do tangential acceleration is sum of forces in the tangential direction. Should I put FT? Divided by M. So tangential acceleration. So sum of force in the tangential direction is just friction, right? So friction over M, which is mu normal over M, which is, well, we just solved for normal. So if you plug that in, it would be mu times V squared over R. Okay, we just did tangential acceleration by typing. Okay, part E, I'm going to abandon ship because we're running out of time and it's really hard to type this one. Okay, we got to find an expression for the velocity as a function of time. Let me get my pen back. I have no idea what just happened. Okay, so we want to do, okay, so this is what we've got, right? Acceleration in the tangential direction is mu v squared over r. It was just asking us for the magnitude, so we didn't care, but now we do need to account for the direction. It's opposite to velocity. But what is tangential acceleration? Isn't it dv dt? Isn't it the derivative of velocity? Boom, we've got a differential equation. You might see on the AP exam, they always say, right, but do not solve a differential equation, blah, blah, blah. Okay, everyone gets so intimidated by that. We just wrote down a differential equation. Okay, now you can impress all your friends. You know what it is. It just sounds really scary, okay? This is a differential equation. We just did it. We wrote it, but we did not solve it. And now we're going to solve it. Okay, separate the variables out. I'm going to put the v's on the left equals negative mu over r dt. Now what am I going to do? I'm going to integrate. I'm going to integrate from v naught to v, and I'm going to integrate from 0 to t. Okay, I'm going to come back over here on the left. So this would be negative 1 over v from v naught to v, and the right-hand side would be negative mu over r t. I'm just going to plug in the limits on the right because it's t minus 0, okay? Okay, just in the interest of time. So then we get negative 1 over v minus 1 over, plus 1 over v naught equals negative mu over rt. And then we're going to solve for v, right? So 1 over v would equal 1 over v naught plus mu t over r. And then if you want, you can, well, yeah, you should invert. So v is 1 over v naught plus mu t over r. And if you want, you can multiply top and bottom by v naught, and you'll get v naught over 1 plus mu t v naught over r. Okay? All right, so that's how it looks for circular motion. You guys can look at this rubric later. We don't have time, but just to watch the recording or take a screenshot and you can watch that later or take a look at it later. That's for the last part. Okay. I just want to emphasize in this rubric, the last point you got was for separating the variables. None of this counted for points, okay? A lot of times we're looking at your setup, your physics. This is math. I'm not saying you're never going to have an answer point, but I'm saying that the majority of the points will be on the physics, okay? So if you feel like you're running out of time, make sure you set up each problem, and you can always abandon ship and come back if you have time to finish it. But I'm just pointing out that there was no credit given for getting to the final answer. If it seems like, wow, this is really hard, come back to it later, okay? Okay, so just to summarize, centripetal force is just sum of forces. That's what centripetal force is. It's the sum of forces. It's not a separate force. When you look at the maximum speed of a car going over a hill, you're looking for the condition when normal is 0. For banked curves, both friction and normal have a component that points toward the center. I'm leaving you with this practice that you can do for homework. You can do it with your teachers. You can do it for homework, okay? And I will see you guys soon. Take care. Stay home, everybody.